Class 6 of optimal design for queuing systems. So in the last class, we saw optimal rates for two different classes arriving to the same system. So now we'll see optimal arrival rates for parallel queues. So first we consider n independent MM1 queues. Whose service rates are mu j and arrival rates are lambda j. J belongs to set of 1 to n. So out of these n independent, j could be one of them. Right. So our first thing is mu j's are fixed and lambda j's are design variable. Right. So and the cost function that we want to minimize is we want to minimize the steady state expected number of customers in the system. Subject to the total arrival rate, that should be some fixed value lambda. So first I'll lay down the problem and then I'll pictorially show how or what is that we're trying to do. So the optimization problem this could be written as minimize summation j equal to 1 to n. The steady state equation with expected number of customers in the system equation for all n servers, but the constraints are n 0 less than equal to lambda j less than equal to j. So each individual servers arrival rate should be less than the service rate, right? So what we are saying is we have n servers with service rates mu j, right? And we have one arrival process lambda with some mean arrival. We must decide how to split this. So there is some setup here which splits the arrivals to all these nodes such that basically this is a closed system. So that the lambda sum of all these is equal to lambda, but the arrival rate is lambda 1 for mu1, lambda 2 for mu2, and lambda j for mu2. We must decide how to split this arrival process among the n parallel exponential servers. Each of these servers has its own arrival. So this has to become probabilistic. And this should be independent of current state and past history of the system. Because it's a design problem, not a control. If this was a control problem, then we would answer the question, how does the past history and state affect the decision that we're making? Okay. So, so what does this mean is each arriving customer is sent to the queue J with a probability AJ, and that is given by lambda J by lambda. So, probability arrival is sent to the Jth, and we know that lambda is summation lambda, right? So AJ will belong to 0. And the jth queue arrival will also be a Poisson process with the arrival rate lambda. Okay, so since it's a constraint-based optimization problem, we'll introduce the Lagrange multiplier here and we'll write the Lagrange. We'll introduce the Lagrange multiplier as alpha and we'll try to eliminate the constraint, right? So the Lagrangian problem now will become minimize summation j equal to 1 to n lambda j by j minus lambda j minus alpha summation j equal to 1 to n lambda j such that 0 less than or equal to lambda j less than mu j equal to set of 1 to. Okay. So now the solution to the above optimization problem is parameterized by alpha. So this alpha would need to have some interpretation as the imputed reward per unit time per unit of error, right? So this problem that we have defined here, and let me call this P1. Okay. So P1 is a separable body. So what does this mean is instead of minimizing the summation, we could minimize lambda j by mu j minus lambda j minus alpha lambda j. Right, says that lambda j is less than mu j. The first derivative of this would be so minus lambda j whole square plus 1 by mu j minus lambda j minus alpha, which is lambda j plus mu j minus lambda j by mu j minus lambda j whole square minus alpha. Mu j, this is, should be equal to 0. This should be equal to 0 by mu j minus lambda j whole square equal to alpha we want to find lambda j. So this lambda j is equal to mu j minus root mu j by alpha plus, right? So this is your optimal solution. So I'll call the lambda j star equal to mu j minus root mu j by alpha plus. Now the point here is what should alpha be? As alpha is a parameter, right? So the solution should satisfy the constraint. And the constraint that we have is summation lambda star j should be equal to 1, right? So that implies summation lambda j star is equal to 1. I'm writing this as an argument of this because we know that lambda j star is parameterized by alpha, which is mu j minus root mu j by alpha. Yes. Okay. So what does this give us? This gives us summation mu j minus root mu j by alpha should be equal to lambda. Okay. So basically the optimal allocation. What is the optimal allocation? So what are lambda 1 and lambda 3? They are those lambda i's which satisfy mu j by mu j minus lambda j whole square is equal to alpha. This one, the first one. Okay. And if lambda j greater than 0 or 1 by mu j greater than or equal to alpha if lambda j equal to 0. For some alpha, such that summation j equal to 1 to 1, lambda j equal to 1. So let us see graphically what this means. So you have the parameter alpha. This is your Lagrange multiplier. And you have your arrival rates. Okay. So Basically, the plots of these would look like this. And then finally, the sum of all these. So this is lambda 1, lambda 2, lambda 3, summation lambda, right? So what we can do is now, given we have some lambda, we draw a horizontal line to this summation of lambda j's, right? Then we draw a vertical line where we find the intersections of all the other points and we find lambda 1, lambda 2, lambda 3. So lambda 2, lambda 2. Okay. So a horizontal line first, then a vertical line to the alpha axis. Where this line intersects the graph of alpha j's as a function of alpha, we obtain alpha j is equal to alpha, lambda j is equal to lambda js lambda. So the optimal value of lambda j for the will be total arrival rate lambda, right? We can also derive an explicit solution for lambda j's in terms of the parameter lambda denoted by lambda js. This is what we want, right? In the following. So first, okay, so to find this, so this is the graphical method. The other method is trying to come with lambda js lambda these solutions, right? So first we order mu j. So we have mu1 greater than equal to mu2 greater than equal to so on till mu1. So lambda as alpha is continuous. Okay, so we have lambda as alpha here. So this is lambda as alpha. So lambda as alpha is continuous and quickly increasing function in alpha, right? For alpha greater than 1 by mu. Okay. In this range, therefore, lambda as alpha has an inverse, right? Which we denote by alpha lambda. We solve for alpha lambda over the intervals induced by 1 by mu1 less than or equal to alpha less than 1 by mu2 or 1 by mu2 less than or equal to alpha less than or equal to 1 by mu3 and so on, right? So now if you see that if alpha is less than or equal to 1 by mu1 and 1 by mu2, then lambda 1 is alpha equal to mu1 minus root mu1 by alpha, right? Lambda j is alpha equal to 0 for all j equal to 2 to 1. So lambda 1 is alpha equal to lambda in this range. So root 1 by lambda equal to mu. So basically, we are equating these two, right? So these two we are but the condition is alpha is in between these two ranges. So we are basically taking some range where only one of the we are taking only one of this is active, right? So we have lambda equal to mu1 minus root mu1 by alpha. mu1 minus lambda equal to root mu1 by alpha. mu1 minus lambda by root mu1 equal to root 1 by alpha. From this we have lambda 1 s lambda for this lambda is equal to mu1 minus root mu1 into mu1 minus lambda by root mu1, which is lambda. But from here, we can see that 1 by mu1 is less than or equal to alpha is less than or equal to 1 by mu2, right? This happens if and only if 0 is less than or equal to lambda is less than or equal to mu1 minus mu1 mu2 root. So basically, this can be written as root mu1 minus lambda by so now we introduce R1, which is 0 less than or equal to lambda less than or equal to R2. We define it such that mu1 minus root mu1 mu2. So lambda 1 is lambda equal to lambda, lambda js, lambda equal to 0. So now the same argument again will continue for all other flows. From this, we'll try to reduce the general form of the solution. In general, we'll define Rk as summation I equal to 1 to k mu I minus root mu I mu k, where k equal to 1 to and Rn plus 1 we define as summation I equal to 1 to mu 1 to n mu naught, right? Now for k equal to 1 to n, if Rk is less than or equal to lambda is less than or equal to Rk plus 1, then lambda js lambda is equal to mu j minus root mu j by summation I equal to 1 to k root mu j mu I into summation I equal to 1 to k mu I minus lambda j equal to 1 to k or 0 but j equal to k plus 1 to n. So basically what we are doing here is, if your lambda is small enough such that it is between these two inverses, then only the optimal allocation would be to allocate only lambda 3 for it and 0 to lambda 2 lambda. Right. As you keep on increasing lambda, you'll see that more and more mm, lambdas are coming up. So what we say is lambda JS is piecewise linear in lambda. So the main observation from this is lambda JS lambda is piecewise linear in lambda. Right. So the note is one side notice lambda JS lambda, once it is positive, right? The rate of increase, the rate of increase is non-increasing. In lambda. Thus, we have lambda JS lambda is concave in lambda greater than or equal to Rj. And the rates of increase of the lambda JS, the rate of increase of lambda JS lambda for fixed lambda is not decreasing in G. So basically, you try to plot this plot every time, and you see that the rate keeps on decreasing as you increase lambda, right? And for different j's, the lambda j is not decreasing much. Okay, so this was for the the optimal solution for splitting of the numbers. So next we have individually optimal equation. Individually optimal equation. So the allocation that we have just spoke now assumes that the allocation of total demand lambda to various facilities is made in accordance with the system objective of minimizing the total rate of waiting per unit time. That waiting per unit time is given by summation j equal to 1 to n Lj lambda j. And Lj lambda j, the formula that we know for MM1 systems was lambda j by uj minus lambda j. Right? An equivalent way of viewing this problem is to visualize each arriving customer having a probability Aj lambda j by j as we defined in the previous of joining facility j, where A prime ij's have to be chosen. Right now, these AIs have to be chosen, not the lambda i's, but uh, there is the okay where this is your decision. So basically, what you have is you have u1, u2, un, and you have your arrival rate lambda, and this probabilistically choose AIs. So this is now your decision variable. But this will affect lambda 1, lambda 2, right? Because change in AI would change the arrival rate at each parallel customer, right? Of joining the facility. AI set by some system, which is some system designer who wants to minimize a steady state expected waiting time of an arbitrary customer. So the cost function remains same. The cost function is summation j equal to 1 to n lambda j by lambda 1 by mu j minus lambda j, which is 1 by lambda summation j equal to 1 to n lj lambda j. So, okay, but this is not as a function of aj yet. So now, but we want to uh, write as a function of aj. So first, let us consider an allocation, some allocation, need not be optimal, an allocation lambda 1 to lambda, right? So once you have this allocation of lambda 1 to lambda n, you can find out the set of joining probabilities, right? A1 to A. From the viewpoint of an individual customer who wishes to minimize his expected reward, expected waiting time under the allocation equation, an arriving customer chooses facility J with probability AJ equal to lambda J by lambda. Conditional on joining facility J. The expected waiting time is, so expected wait times is 1 by mu J minus lambda J for the J. Fixed mean service rate, so mu J is fixed, and the arrival rates lambda J associated with the given allocation are known. The system is steady state, but the exact number of customers at each facility cannot be observed, right? So the customer's unconditional expectation waiting time is therefore, so this is the waiting time. The unconditional wait time is summation j equal to 1 to n aj mu j minus lambda j whole inverse, right? As usual, we call an allocation lambda 1, lambda 1, or the set of joint probabilities A1 individually optimal if no customer acting in its own interest has an incentive to deviate unilaterally from this allocation, right? That is what is known as individual optimal, or it is also known as Nash equilibrium. This will be the case if I know if mu j minus lambda j 1 equal to 1 by mu k minus lambda k for all j comma k such that lambda j greater than 0 and lambda k greater than 0. And 1 by mu j minus lambda j is less than or equal to 1 by mu k if lambda j is greater than 0 and lambda k equal to 0. Okay. Otherwise, okay, so this is your individually optimal solution, right? Uh, if not, then if suppose 1 by mu j minus lambda j is greater than 1 by mu k minus lambda k, then what happens is an arriving customer can reduce its own waiting time by joining facility J, right? With probability AJ prime 0. And joining, so it does not join J because J has a high waiting time. This is the high waiting time of J. This is the low waiting time of K. And joins facility K with probability AK equal to Aj plus ak, the new joining properties, rather than Aj equal to lambda j by lambda and ak lambda k by lambda. So an individual optimal allocation satisfies the following conditions. So what are the following conditions? Wj lambda equal to 1 by mu j minus lambda j equal to alpha if lambda j is greater than 0. Similarly, Wj lambda j equal to 1 by mu j greater than or equal to alpha if lambda j equal to 0. For some alpha equal to For some alpha greater than 0 such that summation j equal to 1 to n lambda j equal to lambda. So we would like to compare such an allocation denoted. So this is the individual optimal allocation. So we'll denote them by lambda j e alpha or lambda j e lambda, depending on what we are parameterizing. So these are your individually optimal allocation, and these are your lambda j s alpha and lambda j s lambda are your socially optimal allocation. Okay, these two we have derived in the previous part. These two we'll talk about, right? So the individual optimal allocation, these two equations, what it does is it equates average cost, that is 1 by mu j minus lambda j, or the internal effects, whereas the socially optimal, the one which we allocation that we defined previous, equates marginal cost, that is mu j by mu j minus lambda j whole square, right? So internal effects plus external effects at all facilities. So in terms of alpha, the individual optimal cost would be is equal to mu j minus 1 by alpha plus j equal to 1 to 1. So similarly, again we will so again in the same way that we have done the previous socially optimal allocation, we'll again do that, but now we'll have, instead of defining rk that we defined previously, we'll have sk which is defined as I equal to 1 to k mu y minus nk equal to into n, right? And Sn plus 1 equal to summation I equal to 1 to n mu 1. And the so this was your socially optimal allocation, right? I'll write the individual. So this is your individually optimal allocation, right? So here also the same notes will follow. So the positive lambda j e lambda, which is the individually optimal allocation, are piecewise linear in lambda with non-increasing slope. The slopes are positive for lambda j e lambda are equal in the case. Okay. So the general observation is that individual optimal allocation assigns more customers to slower services, to faster services, right? So servers which are faster, they'll get more customers, and servers which are slower will get less servers than the socially optimal allocation. More specifically, the individual optimal allocation always assign more facilities to the fastest one and fewer arrivals to the slowest, right? As lambda increases, facility the slower one would receive fewer and fewer, and the faster will keep on receiving more, right? Mm, yeah. So that is how these two are compared. Okay. So this was so this completes one part of our class, that is the introduction to design models. So in this, we have seen how to actually design a model, come up with an optimizing solution, and so forth and so forth. So next, we'll look at some other different types of problems in queuing systems. So here everything so was on queuing systems, but now we'll consider uh, a more different approach where I'll give you an example. So we'll do a more scheduling problem, right? So in the previous case, what we saw was we saw that uh, uh, we saw how arrival rates and service rates affected the uh, quality of service, or how the system performs. But now we'll try to find how does scheduling affect the system and its metrics, right? So first I'll give an example of this. Example would be a simple wireless uplink, right? So the problem here is you have a receiver and you have two queues, Q1T and Q2T. So arrivals happen A1T and A2T. Okay, so now here for the scheduling problem, I'll be switching to discrete time. And I'll be more focusing on the control problem than the design problem. So more on control problem than the design problem. Okay, so you have S1T and S2T, right? So now your T here is slotted time. So this is some slotted time. At every slotted time T, A1T and A2T with the A1T comma A2T is a vector of new arrivals on slot T in units of bits, right? The data is stored in the queues Q1T and Q2T and await transmission. So we assume that the receiver coordinates traffic decision every slot, right? Channel conditions are assumed to be constant for that slot because we are assuming wireless, but they can change from slot to slot. So okay, so we have one here. So S1 and S2T are channel condition. So the channel condition represent any information that affects the channel on slot T, such as some coefficients of which are fading or noise ratio and other. We assume that network controller So some other third party can observe ST at the beginning of each time slot sleep before making the transmission relation, right? So the channel level scheduling is called opportunity scheduling. Uh, every slot T, the network controller observes the current ST and chooses a power allocation vector PT. With some set of possible power allocations, right? Now, this decision together with the current ST determines the transmission rate vector B1T, B2T for slot T. So basically, B1T is some function of the power allocation vector and the channel condition vector, right? Similarly, B2T is a function of power allocation vector and state condition. Okay, these closed form solution depend on what type of modulation, what type of coding strategies, and all that you're using uses. But the point that we are interested in is the queuing dynamics, right? So the queuing dynamics QK T plus 1 is max QKT minus DK hat PT ST 0 plus AKT. So this is the kth queue. The next interval would be how much has arrived, my subtracting how much has been served from the previous, right? So now we'll try to design an optimization problem, but this will be a time average case because we are considering decision at each time slot, right? At each time slot, we'll make a decision which channel to send, or maybe we'll try to find the power allocation or the hmm, yeah, similar. So let PK be time average power expenditure of user K, right? So basically, PK hat is defined as limit t tends to infinity 1 by t summation tau equal to 0 to t minus 1 pk tau. So the problem of designing algorithm to minimize that average expenditure in the Q stability with written as minimize P1 hat plus P2 hat such that 1. So I'll be just writing in Qs are stable. PT belongs to power allocation set for all t 0 1. Right. So this Q stability, till now we have just assumed MM1 system and we've assumed that for lambda less than mu, Qs are stable and then there exists a steady state thing. But if they are not MM1 or if what, then how to deal with the constraint of Qs are stable or not, how to mathematically write down the stability of Qs, right? That we'll talk in the next class. Q stability, what it ensures is the time average output rate of the Q is equal to time average input, right? So we'll try to come up with simple algorithms that makes a decision, each time decision at every slot, like power transmission decision, without requiring any a priori knowledge of probabilities associated with the arrival or channel process, right? Before what we used to do is we used to know the probabilities of the arrival process and the service process, but now we'll not know what the probabilities of the arrival process and service process are. Without knowing those, can we take a decision, right? Yeah, so we'll be looking into similar problems in the next class. So I will stop.